So without any further ado, over to Dr. Parra.
Thank you. Let's start with the mic check. Can everybody hear me in the back? Excellent. All right. Well, Pat, thank you very much. I am not Howard Schlossberg, but I'm going to be playing him for the purposes of the talk today. And it's my pleasure this afternoon to talk to you about our AFOSR portfolio in lasers and optics. Let's make sure that this works. Like I said, this is really Howie's portfolio, and the description, as the title implies, is pretty straightforward. We're looking at basic research in lasers, optics, and their applications. The sub-areas in the portfolio, obviously, lasers is one of them. Now, these are going to be sort of medium-sized to large-sized laser architectures that we're interested in, nonlinear optics, laser-matter interactions, as well as microsystems. So before getting into sort of the details of the portfolio, Dr. Schlossberg really wanted to take an aside right at the beginning to sort of honor one of the pioneers in the field of lasers and optics, Dr. Anthony Siegmann, who unfortunately passed away last November. Like I said, Dr. Siegmann really, in many ways, was one of the great giants of this field. He was a longtime PI and friend of AFOSR, and in fact, here he was our featured speaker at our Laser Fest event back in 2010, and this picture is of him giving that talk on that day. Here's also another picture of him with our very own Dr. Russell. So Dr. Siegmann, he's probably best known for writing the book on lasers. And this is, in fact, one of those instances when people say, oh, I wrote the book on with capital T-H-E. This is true. He actually wrote sort of the Bible on lasers. In fact, all of us, that's how I first knew of him, because of having to buy this expensive, by the way, book. So it's still on my shelf. I haven't gotten rid of it. It's actually probably a little too pristine. I should have maybe read it more. In any case, Dr. Siegmann is also, from a technical perspective, very well known for, really, he invented the concept of it, the unstable laser resonator, back when essentially laser had just started. He also was instrumental in really bringing some rigor into defining concepts such as beam quality. In fact, he had the first sort of mathematically rigorous definition of what beam quality is. It's known as sort of this M-squared metric, if you've heard of it. And in fact, this is now standard parlance in lasers. And then he was very much the pioneer of techniques that ultimately led to sort of ways to characterize ultra-short pulse lasers. So with that said, now let me begin sort of the portfolio discussion. And we're going to talk about lasers, all sorts of lasers, big, small, expensive, cheap. And here's two pictures of two different types of lasers. So on the left, you see this is a typical diode laser that you would find on a CD player. In fact, most of the laptops that are in front of you have things that look like that inside. And these are roughly 50 cents a piece, to give you a sense. On the right-hand side, we see a part of it, the Wiggler section of an X-ray free electron laser. This is the LCLS at SLAC at Stanford, if you want to know. And the actual laser itself is 2 miles long. And so this is just a little section. And this is roughly $500 million with a capital B dollars. So 50 cents, $500 million. And there's everything in between. And that's what we're interested in. So here's a little more details on what the portfolio entails. At the very top, we're going to be looking at things such as high average power solid-state lasers. Now, these are architectures that really end up having powers on the greater than 100 kilowatts and more. That's sort of what the interest is. In terms of an application, these are the sort of systems that you would think of for sort of directed energy type of applications. In particular, I like to point out the first bullet here, ceramic laser solid-state materials. This is done in close collaboration with Dr. Sayer. Then we're also going to be looking at what Dr. Schlossberg calls modest power lasers. So these are going to be smaller architectures, typically powers that are like on the 1 watt to possibly up to 1 kilowatt in range. Many of these will work sort of in the mid-infrared region, and they're interesting for that. And typical applications for things like that would be in sort of remote gas detection, and in fact, even spoofing heat-seeking missiles and things like that. Then there's a section of the portfolio involved in nonlinear optics. Concepts such as nonlinear frequency conversion, as well as ultra-short, high-intensity pulses. Now, I'll point out that this little bit has actually sort of spun off back October of last year, and it's now really its own portfolio. And you'll get to hear a lot more of that portfolio tomorrow morning at 9:15. And I've heard that that's supposed to be a pretty good talk. So if you can make it, I encourage you to do so. And then we have, what's that?
Who's going to give it?
A bright young guy, I heard that. And then we have a little section on microplasma arrays, and this little bit is actually done in close collaboration with Dr. Lugansland. Okay, so recently, AFOSR funded a study to look at 6-1 opportunities of high energy and high power lasers. And we were quite pleased to see that the recommendations that came out of this study were very well in line with the things that we had been funding. So for example, just to call out, there were 3 sort of technical points that were made. 1, looking at ceramic solid-state laser materials. 2, looking at fiber lasers. And then lastly, looking at ultra-short, high-intense pulses. So in some ways, the theme of this portfolio, to sort of help you understand, is we're really interested in looking at architectures that are both high efficiency, that have high efficiency, as well as high beam quality. So what we're really interested in doing is we want to take sort of the electricity that's coming out of the wall plug, take those electrons, turn those into photons. So that's kind of sort of part of the efficiency part of it. Normally, these photons don't have the greatest beam quality, but we're interested in delivering these things out of range. So that's where the sort of the high beam quality concepts come in. And oftentimes you'll find that these architectures that we're toying with, in many ways, are simply an exercise in mode conversion. And what I mean by that is essentially taking sort of low beam quality out of the wall, if you will, and then making that have high beam quality so that we can deliver them downrange. Okay, so here's the agenda. It's sort of 2 parts. We're gonna look at 5 research highlights, 2 that sort of would fall under the category of high average power lasers, 1 that's sort of the modest power laser concept, and then these 2 here that are in the sort of the nonlinear optics. And then at the very end of the talk, I want to talk about 2 quick examples that would be sort of technology transfer. So let's start with the first one, ceramic lasers. So ceramic laser gain media. So this is a very interesting concept. So it turns out that using gain media made out of ceramics, as opposed to the conventional gain media, which would be sort of single crystals and glasses, offer a lot of interesting advantages. So right off the bat, you can make these things into arbitrary shapes and sizes. And that alone is actually quite remarkable. But if that's not enough, you can actually sort of have different components, make a composite gain media where you have sort of different doping levels and even different dopants, and just put this together as one laser system. And then on top of that, you can actually have spatially varying doping profiles in one single piece of material. So this is something that you just couldn't do before this. So this is a brand new sort of degree of freedom that this opens up in terms of sort of the laser design. You can achieve things like higher doping concentrations without adversely affecting your laser efficiency. And then you have some interesting materials such as these quiyoxides that typically are very difficult to grow in single crystals that you can now have a chance to maybe put them in ceramic form. We have a number of efforts in this area. Many of these efforts, in fact, are done in collaboration with sort of the Joint Technology Office. We fund Dr. Ikesue as sort of our first bullet here. In many ways, he's sort of been sort of the father of this particular field. He was, I think, the first person to really put ceramics as gain media sort of on the map. Then these materials, these quiyoxides, are looking very promising. This is done, again, in collaboration with Dr. Sayer. We fund folks at Stanford, Dr. Robert Bayer, to look at a whole different assortment of dopants. Some of that work is done in conjunction with the University of Central Florida. And then we have new young people. We have a YIP, Dr. Wu, who's looking at materials that are these hydroxyapatites. Now, these are interesting because, in fact, your bones are made out of hydroxyapatites, as I just found out. And people use this for all sorts of applications, some of them even medical. In fact, they use these materials to coat sort of artificial bones and things that you would put in your body, like hip replacements and so forth. So here's a picture of Dr. Schlossberg at a meeting in Japan, the ceramic research meeting in Japan. And in fact, sort of behind him is Robert Bayer, and in the back to the right, if you're looking at the picture, that's our very own Ken Goretta, the director of AORD. So I asked Dr. Schlossberg, I call him Howie. So I asked Howie, I said, Howie, why is this picture here? What is it that you want me to tell? What's the point, right? And he said, well, look, Rick, I try as often as I can, as many times as I can, to put this picture in all my presentations. And I said, well, why? Why is that? I was like, it's because I look really slim in it. So that's what you're supposed to take out of this. In addition to the fact that, of course, we collaborate very heavily with our international partners. But he does look good here, I should add. So that's sort of the ceramic piece. So now let's move on. Let's talk about the second example in the high average power lasers. In fact, a concept known as XPOWs. But by way of introduction to X-Pulse, let me sort of talk about something called D-Pulse. Now, D-Pulse, this stands for Diode Pump Alkali Laser System. So this is a laser architecture that's gas-based, an alkali gas. The concept's been around for a little while, back to, I think, at least 2004. So in this case, we're looking at cesium, and this offers two sort of interesting advantages. The first one is that you can pump it with diodes, and that's big. In fact, you can actually pump it with very energetic diode bars and stacks. So that's advantageous. And then second of all, it's potentially an architecture that would have very high efficiency. In fact, it's got a very low quantum defect, and by that I mean it's really the separation of these two upper states. It's a three-state laser where you pump, so in this case, we'd be pumping sort of in the D2 line of cesium to the upper state, and then it relaxes to the one state, and then you would lay sort of on the D1 line. The fact that these two upper states are close together, that's what we mean when we refer to a low quantum defect, and that means that this thing's very efficient. In fact, you know, if these things are almost the same, that means that most of the energy that you're putting in, you're getting back out in the laser. So you want these things to be as close as possible together now, but you don't want them to be too close, right? Because if they get too close, in fact, close enough that it gets on the order of about sort of kBT, sort of the temperature of your laser, then you're going to get things like thermal mixing, and in fact, it stops working. In fact, you know, lasers work when things have a pretty good direction. So if you undo that, you get into trouble. So that's one point. So this is an architecture that a lot of people are looking at. In fact, our RD is looking into it. Folks at the Air Force Academy are looking at this. But it has one problem, which is since it's an atomic system, this line width is actually fairly narrow. It's a very narrow line width. So that means that if you have a sort of a somewhat broad pump, most of your pump actually just goes through and gets wasted. So in order to sort of address that, we have this concept called X-Pulse. So in X-Pulse, what we've done is we actually introduced a rare gas, in this case argon, and then you have sort of these cesium-argon pairs that have these very weak molecular interactions, but strong enough that they actually modified the level structure. And in this scenario, you would pump, sort of in this picture, you would pump, say, so now we've changed the wavelengths a little bit, we pump, say, at 837 nanometers, and then you get your lacing to happen, in this case, at 852. And you see that little delta E between the upper states is shown here. What's interesting, and here's my animation, so this is my movie. This is my exciting movie that I have in here. So in fact, it's so good, let's actually do that again. So you see that you can actually pump at a whole different set of wavelengths. And in fact, the height of this arrow corresponds to the wavelength. That's the way to think about it. So that's kind of interesting, because now you've effectively broadened the line width of your laser, hence resolving the problem that I mentioned. Now, one drawback is that I'm going to do it again. If you look up here, you see this delta E. Obviously, as I get closer to my lacing wavelength, that delta E gets smaller and smaller and smaller. And that's why I made that earlier point that might have made no sense about, like, well, how close can you get them? Who cares, right? Well, it turns out that you actually care, because you want to figure out, okay, well, how close can I make it? So folks have been looking at this, and it turns out that the answer is 0.7 kBT. Now, that's really all I can say about it, but I like to quote Howie when I asked him, oh, so that's interesting. So what does that mean? He said, well, Rick, the way to think about it is, like, if you get below 0.7 kBT, it all goes to hell. So that's sort of a takeaway. So let's move on. So that was the high average power laser architectures. Now we're going to talk about sort of the modest power. And in this case, we're going to talk about something called a photonic bandgap gas laser. So this is, in many ways, a new class of laser altogether. It's really kind of a hybrid laser. It's got components of a gas laser. So these are molecular gases that you're going to use. Acetylene, I believe, is what these researchers are doing, which have the potential of exceptionally high quantum efficiencies, albeit you have very small absorption. So that's a little bit of a problem. And it has elements of a fiber laser in that, in fact, there's a fiber in there. So you have the advantages, the fact that you have very long interaction lengths, and that kind of offsets the small absorption, because now you have a long path where you can interact. And because of the geometry of fibers, you get beam quality, high beam quality, almost for free. Now, these are not any standard fibers. These are, in fact, photonic bandgap fibers, which means that they're hollow. So they have a very interesting structure. Unfortunately, we don't really have a picture of what a cross-section of this thing will look like, but it's effectively a hollow fiber with sort of a structure implied with tubes and so forth that allows for the guiding of both the pump light and the laser light. So in this scenario, you would pump roughly at about 1.5 microns, and then you get this thing to laser roughly 3 microns. So here's another interesting benefit, that now you can actually access sort of the mid-infrared wavelength. So this is the concept. This is an effort led by Dr. Corwin out of Kansas State University. This is done in conjunction with the University of New Mexico, as well as the University of Bath, who provides these very exotic fibers, and these fibers are quite remarkable. And in fact, initial experiments show that this actually works. So if you look at sort of the manifold of different levels that you can look at, you see that you have a whole host of potential lacing states. You can access things as close as 1.7 microns to your 1.5 pump. So that would be one that would be actually probably very efficient, right? But then you have a whole bunch of them that sort of are in the sort of 3.1, 3.8 microns, sort of in the mid-IR. And in fact, you can even have some lacing states that would be in the 8 micron and even the 13 micron. So potentially, you can think of this as something that could get you sort of in the long wave IR regime. So the takeaway of this is that they're looking at it, it works. This is an architecture that essentially makes somewhat practical systems that prior to that, because of the small absorption, you would not have really considered. So by putting it in these sort of exotic fibers, now they become more relevant. Okay, so now I want to switch gears again, and I'm going to talk about sort of the nonlinear optics part of this process. So in fact, I'm going to tell you about a very interesting concept. This is an effort out of the University of Michigan, and they're interested in creating compact, on-chip emitters of extreme ultraviolet light. So let me say that one more time. Compact, on-chip emitters of extreme ultraviolet light. So if you're familiar with the field, you know that if I want to create extreme ultraviolet, typically I have sort of this bulky laser. It's a high-intensity, high-peak power laser, which are awesome, as you'll hear tomorrow. But you have this big, bulky thing. It's kind of expensive. And then you sort of focus all that light to very high intensities, typically on a gas jet. Typically, you have xenon coming out of it. And then you get, via a process known as high harmonic generation, which, again, you'll hear a lot about it tomorrow, you get this ultraviolet light, extreme ultraviolet. And in fact, you can push these systems to go all the way to soft X-rays and hard X-rays. So very exciting work. And that's how we do it. So here's a scheme where they're going to actually leverage these microresonator toroids, and you're going to pump them. It's hard to see on the slide, but you're going to pump this with just CW infrared light. And that pump laser normally doesn't have a lot of intensity. But this light, because this microresonator really is kind of a very high Q cavity, that light's going to circulate inside there. And it's going to build up. It's sort of like almost like a power enhancement cavity. And it's going to sit around and circulating. So inside the device, you're going to start building up this intensity. Then you're going to fill sort of the exterior of this with your xenon. So this is the xenon that ultimately be the one giving you the high harmonic generation. So you have sort of some background atmosphere of xenon. And then you're going to take a gold nanoparticle, and you're going to put it on that microresonator. And via plasma enhancement, it turns out that you can, given the calculations, you can couple the light that's circulating inside your toroid on the surface of this nanoparticle and achieve extremely high intensities. In fact, intensities that they project are high enough to actually generate the extreme ultraviolet. So the idea would be that at every half cycle of your driving laser, so this is your infrared laser, which again is CW, it's not pulsed, you're going to get a little burst of XUV coming out of that. So this is very interesting if it works. We're hopeful. And in fact, this is a team that they are experts at making these microresonator toroids. They've been doing it for some time. And in fact, they've also been involved in using these devices to do nonlinear frequency conversion. Like a few years ago, they actually used these devices to generate a couple of processes such as third harmonic generation and things such as third order sum frequency generation. And most recently last year, and there's a whole bunch of publications, they were able to achieve fourth harmonic on these devices. And now this is, again, it's hard to see it, but this is roughly slightly less than 400 nanometers in wavelength on chip. So this is very interesting work, and we're very hopeful. Okay, so now I'm going to switch gears one more time, slightly. This is still sort of a nonlinear optics part of the portfolio, and we're going to talk about pulse lasers. So traditionally, if you want to have a pulse laser, you have a laser cavity that supports a whole bunch of modes, and then you put in an intracavity element known as a mode locker. And what this does for you is it takes all these modes that have different wavelengths, and it generates a phase relationship between them. In fact, it locks all the modes together. And it turns out that the output of such a sort of mode-locked laser is a train of ultra-short pulse lasers. That's sort of the basic way you make these things. So we're going to try to do the exact same thing, but without having sort of this mode locker and the feedback. And we're going to do it in a really sort of at least at first, unusual way. We're going to take individual lasers, in which, in this case, there are this blue bar and this green bar and the red bar, and this implies sort of a laser diode bar, but it doesn't have to be. This, in principle, could work with sort of separate, bunch of fiber lasers, for example. And we're going to have all these lights that have different wavelengths, and we're going to combine them using a dispersive element. Now, this dispersive element, think a grating or a prism. We're just going to take all these wavelengths and we're going to combine them into a single beam. So this is a spectral beam combining, which people have been doing for a long time. This is nothing new. And we're going to pick off a little bit of this, and then we're going to feed it back with a feedback loop onto our original lasers, and we're now going to control the phase of these lasers. So again, we're doing both spectral beam combining, and now we're doing coherent beam combining by manipulating the phase. And in doing so, and if we set up this phase relationship that I talked about, what you should get out of here, it will be pulses, potentially very short pulses. Such an architecture, which sounds pretty interesting, it's intrinsically very scalable, possibly reconfigurable, but I think this last bullet, which I don't think anybody out there can see, is the fact that now you can think of this being a scheme to generate short pulses in systems and spectral regions that prior to this you just couldn't do. So this is why it's potentially interesting. Now, a little small aside for those of you guys who like optimization problems and so forth, it turns out that conventionally if you wanted to do coherent beam combining, and you have, say, n number of lasers that you're trying to control, you need to make n number of phase measurements. It turns out that they're using an algorithm which has been around for a little while. It's known as stochastic parallel gradient descent algorithm, mouthful. It turns out that if you use this, you only need to make a single phase-sensitive measurement. And using that single phase-sensitive measurement, you get all the information you need, and you are able to lock these lasers together. Now, this is, and then they have some modeling that shows that this works. And if this works, then now you have a pathway to potentially control a large array. Whereas before you would need tons and tons and tons of measurements. Now you could do this. So that's why this is potentially very interesting. OK, so those were the 5 sort of research highlights of the portfolio. And now I'm going to talk very quickly on 2 examples of technology transfer. The first one is something known as dual comb Fourier transform spectroscopy. So, and comb here means frequency comb. So it's dual frequency comb Fourier transform spectroscopy. So if you're familiar with Fourier transform spectroscopy, this is essentially doing spectroscopy not in the frequency domain, but sort of in the time domain. And in principle, you can go back and forth and get the same information. Now, conventional Fourier transform spectroscopy has a moving components in there. In fact, you have sort of these rotating mirrors, and it's these rotating mirrors that give you the time delay that you need. Now, because you have a mechanical part, now you have certain limitations as to how fast can you take data and sort of the dynamic range and the sensitivity ultimately of your spectrometer. So here's a scheme that was obviously funded as basic research a while ago, and that AFOSR is now involved in helping transition this. Without going too much into the details of the scheme, you have sort of 2 femtosecond lasers. So these lasers, again, emit a train of laser pulses. And one of them has a slightly different rep rate. Okay, so they're essentially identical, except one has a slightly different rep rate. And when you combine these things, what comes out of that is now a train of pairs of pulses. Because again, you have these 2 things. But because one has a different rep rate, these 2 pulses, in fact, I think in the picture you can see that sort of the first pair, it has some separation. And as you go and you look at subsequent pairs, this separation gets smaller and smaller and smaller. They eventually overlap, and then they pass each other. So now you built in, without any moving parts, a time delay. So this is why this is very interesting. And a lot of people are looking at this for as a real enabling technology where there's no moving parts. Your speed at which you take data has now increased, and your sensitivity potentially is a lot higher. So that's that one. And now let me talk about optical coherence tomography. Now, this is in many ways, I think, a textbook example of how do you go from basic research to an enabling technology to an industry. This was originally invented with AFOSR funding back in 1986. And optical coherence tomography, if you're not familiar, it's an optical diagnostic technique. Without going into these particular details, suffice it to say that what you're doing is you're leveraging the coherence that comes with your laser, and you're essentially, this thing's typically used looking at a surface, and you launch your laser wavefront into a surface, and then you sort of pick back, sort of the returns of different layers, and then you can do a tomographic reconstruction. So you end up getting depth information out of using this. And in fact, here on the bottom right, you'll see sort of, this is what an actual product, an actual OCT device would look like. Now, most of the applications of this technology have been sort of in the medical field. So you routinely now see devices such as this in sort of hospitals. So in fact, you know, once this thing was sort of developed, there was a lot of things that happened. I mean, and things like Doppler and polarization-sensitive OCT were additional techniques that brought in sensitivity. And then there were additional things such as swept source OCT and spectral OCT that then really gave this the real power, because now you increase the speed and now you increase the resolution, and people got really interested very fast. So these things are used, for example, in the military to look at sort of skin and making burn depth measurements, looking at blood flow, looking at airways and seeing damage in airways, and I'll say more in the next slide about that example. And then, but really it's in the civilian world where this thing has taken off. One of the first uses was really looking at eyes and problems with your eye. You can now actually look inside arteries and diagnose diseases, as well as look down your esophagus and do some of the same thing. In 2010, there were about 16 million eye diagnostics done using this technique, which again, I'll point out that was invented with AFOSR funding. And to date, there's been about 50,000 coronary artery procedures to date. So to further highlight the impact of such a thing, let me talk about one specific example. So it turns out that 27%, about a third of Army burn admissions suffer inhalation injuries that go completely unchecked. You just don't spot them. Now, why is that interesting or relevant? It turns out that patients that have this inhalation injury, when they come in, they have 10 times the mortality rate than people that don't. But there's no technology to provide the early diagnosis, because if you could spot it right away, then there's a whole bunch of things that you could do to solve the problem, like mainly give them oxygen and things like that. So OCT imaging is a candidate to potentially provide this early detection. So this is roughly what an OCT image would look like. You know, you put it on a catheter, you send it down wherever you want to look, and sort of the light goes around in 360, and you get sort of this tomographic image of whatever tunnel you're in, and you get sort of depth information. So here on the left, on this picture on the top, this is what a normal airway would look like with depth. So we're looking sort of at the surface and into it. And the bottom one is what an inflamed airway would look like following sort of a smoke inhalation. So this is very interesting, and it seems that, you know, OCT may provide sort of the high resolution, the 3D imaging capability that you need to maybe solve some of these problems. And I think right now these things are being proposed for clinical trials. Now, this is actually my last slide, so I'm going to end on this one. But here's an example where OCT is being used for this intracoronary artery evaluation. And in fact, folks that do this, and it's not really easily seen on here, but I think you can see a little better on the side screens. You know, they're looking at this as really being the next major sort of imaging modality in this field. So this is sort of what you're seeing. You put in your OCT device, and then you move it down the artery, and you can actually make a three-dimensional picture of what your artery looks like, and then you can then, via some algorithms, then compute and identify different things that are going on. So in fact, here you see these little white spots are calcium deposits, and you can spot them right away. You can identify plaque, you get some lipid deposits, I think, over here. And so you can actually see these things way before you would have a heart attack. And in fact, people use this to guide, you know, the insertion of stents. So in fact, this blue grid that you see over here, that's a cross-section of a stent inside this particular artery. So this is very interesting, and again, I think that the point of bringing this up, the reason I think how we wanted to put it in is because it's really, I think, a textbook example of how do you go from very basic research to then sort of what people would consider as an enabling technology, and then it becomes an industry. And probably many of us in our lifetime will have an OCT scan done at some point, is my guess. So with that, I conclude. Thank you for your attention, and I am happy to take questions for Howie to answer.
Thank you, Dr. Parra, for
I mean, I could
giving
answer
that
some
talk.
questions, maybe.
We can try and answer some questions, but of course, we'll if we can't answer them, we'll certainly collect them and get them to Dr. Schlossberg for his answer, as long as you give us your contact information. So are there any questions? Maybe there aren't any. Yeah, hang on.
I guess you talked about in the photonic bandgap lasers going to the LWIR, and I'm just wondering what the benefit is to that. Is there some special need to have an LWIR laser? So
that's a good question. I would suggest that maybe Dr. Schlossberg will give you a better answer, but I think it's a spectral region that I've known that a lot of people are interested in that. I think sort of from a remote gas detection perspective, there's a lot of transitions over there that have much higher signatures, that if you wanted to do that in the visible, you would have a real hard time. So that's sort of my quick answer.
Any other questions? Okay, let's thank Riq.
Thank you.